we have seen the choice of the basis for the various subspaces that we had considered connected with a matrix. We shall now go back to the various fundamental questions that we raised in the first two lectures and setting our goal for the course as finding the answers to these questions. Now, let us go back to these questions and see whether we have found all the answers. The first question that we looked at was, suppose A is an m by n real matrix and B belongs to R m, and we look at the system A x equal to B. So, given B, we want to find x in R n such that A x equal to B. So, the first question was under what conditions that this is possible. So, the question that we raised was what are or what is the conditions, if any, that B has to satisfy for the system A x equal to B to have a solution, and any such condition will be called consistency condition. This is what we called any such condition which guarantees the existence of a solution is called consistency condition. So, what we are asking is what is or are the consistency condition. So, the question is what is or are the consistency conditions, condition or conditions, whichever way, depending on how many condition we have to satisfy. So, this was the first fundamental question that we raised. Now, during the course of our discussions, we found the answers to this question by interpreting it in various formats. So, the answer to this question that we found was in many forms. The first form was that the rank of the matrix A must be equal to the rank of the augmented matrix. Recall that the augmented matrix is the matrix obtained from A by appending as a last column the vector B. We got these conditions when using elementary row operations. This was the first time we got the consistency conditions for the system to have a solution. Then we looked at them in the point of view of transformations, and we observed that if A x equal to B has to have a solution, B must be of the form A x, and such vectors are called range vectors. So, the other way is that B belongs to the range of A. So, this was one, or looked at another manner, the same thing equivalently can be stated as B belongs to the range of A. Or now, we found that the range of A is the orthogonal complement of the null space of A transpose, and therefore, B has to belong to range of A simply means that B must be orthogonal to all the vectors in the null space of A transpose. So, the same can be written as B is orthogonal to all vectors in the null space of A transpose. Now, a vector is orthogonal to all the vectors in a subspace if it is orthogonal to all the basis vectors, and therefore, this can be stated equivalently as B is orthogonal to all vectors in a basis for NA transpose, or in particular we can state this as by choosing the basis to be an orthonormal basis, it should be orthogonal to B psi j equal to 0, where psi 1, psi 2, psi nu A transpose is an orthonormal basis for null space of A transpose. So, the answer to the first question, what is or what are the consistency conditions, we found the answer in many formats, all of them are equivalent, and finally we boiled down to the format phi, which told us how to analyze these spaces. Then, having found the consistency conditions, then the first thing that we would do is, given any B, we shall ask, does B satisfy the consistency conditions? That was our next question, and we said we could get the answers to this in two forms, either yes or no. Either B may satisfy the consistency conditions or not. If B satisfies this orthogonality to all the basis vectors, then it satisfies the conditions. If it fails to be orthogonal to even one basis vector, then it fails to satisfy the consistency conditions. Now, in this case, solution exists, solution to system A x equal to B exists. Then we ask the question, how many? We now know that we have found the answer that either unique or infinitely many. Then we ask the question, when is it unique? And now we have the answer that when the rank of the matrix is equal to n, the number of columns, then solution is unique. Then finally, we ask the question, in that case, what is the solution? And now we know the answer, the solution is given by our representation that we got x is equal to summation j equal to 1 to rho 1 by S j b u j v j, where u j, v j, S j are, as we have found out, the singular values, the basis for the range of A transpose, etc. So, we have the answers for all the questions that we asked in this case, the case where we have unique solution. Then similarly, we asked, when it is infinitely many, when is it infinitely many? And uniqueness we got when rho equal to n. So, it should be the other case, the rho cannot be greater than n. So, this can happen when rho is less than n. Then solution is then infinite number of solutions. Then we asked what are all the solutions. And now we know the answer, that they are all given by x equal to summation j equal to 1 to rho 1 by S j b u j v j plus summation alpha k phi k equal to 1 to nu a, where alpha 1, alpha 2, alpha k arbitrary. Then we asked for unique representative solution. Is there anything like that? And we found that that is given by x optimal, which is summation j equal to 1 to rho 1 by S j b u j v j. So, thus we have all the answers to all the questions in the case B satisfies the consistency conditions. The next case that we have to deal with is what happens when the consistency conditions are not satisfied. Then we found, so we asked the question, what can we do? Well, first of all, we get the statement that there will be no solution. So, first let us note that down, there is no solution, there is no solution. So, we said if there is no solution, what can we do? Then we observed that we can find least square solutions. We can find least square solution, that is solutions which are very close to B and minimize the error. We can get as close to B as possible, and the solution which gives you the minimum error is called a least square solution. Then we ask, if we can find least square solution, how many? Again we had the same situation as before, either unique or infinitely many. Then we ask, when is it unique? Now we know the answer, that we get the unique least square solution when the rank is equal to n. So, when rank is equal to n, least square solution is unique. And then once you know that you are in the case where you have only least square solution and that least square solution is unique, we ask what is the least square solution? What is this unique least square solution? And we know the answers from our analysis, that that is given by x l equal to summation j equal to 1 to rho 1 by S j b u j v j. So, now we have all the answers in the case when B does not satisfy the consistency condition and we have unique solution. The next, so we have this situation covered. The next series of questions that we raised were in the case of infinitely many solutions. So, when the question therefore is, when do we get infinitely many solutions? Then we know that when rho equal to n we get unique, the other two cases are rho greater than n and rho less than n, but the rank cannot be greater than n as we said before. So, we get when rho is less than n, we get infinitely many least square solutions. what are all these solutions? What are all these? Least square solution. That was the next question that we asked. Now we know how to get all these solutions are. They are given by x equal to summation j equal to 1 to rho 1 by s j b u j v j plus summation k equal to 1 to nu a alpha k phi k, where alpha 1, alpha 2, alpha k arbitrary. So, then we ask, what about a unique representative? And we had the answer, we had x l optimal, the least square solution optimal, which is given by j equal to 1 to rho 1 by s j b u j v j. So, thus we have the answers to this entire series of questions that we raised about a linear system of equations. We have the consistency situation, the non-consistency situation, consistency unique situation, consistency non-unique, inconsistent unique least square, inconsistent infinite least square. In both the cases, consistent and inconsistent, when we have infinite solutions, we have a corresponding optimal solution. And thus, we have therefore, finally, our answer was, in all these cases, we call the answer we got this one and this, we call this as x sol. In all these cases, the final version of the solution, the best possible solution that you can get for the system A x equal to b. When I say best possible, I mean it is either a solution, and if you can't find a solution, least square solution, and if there are many solutions, it has the least length. So, least length, least error solution is called x sol, and we have x sol is equal to A dagger b, where A dagger was the matrix summation j equal to rho 1 by s j v j u j transpose, and this we called as pseudo inverse. This is called the pseudo inverse of the matrix E. This was the first set of basic questions that we raised about a matrix A. It is about the non-homogeneous system of equations, consistency conditions, about the existence of solutions, uniqueness of solutions, when it is non-existence what can we do, and whenever we do that approximations, will it be unique, infinitely many, and what is the most representative solution. So, we have the answer for all these questions, and we put them all in a single package. Whatever case you are in, just compute A dagger b, and that will be your final answer. Whichever of the 4 cases we discussed, in all these cases the final answer is going to be A dagger b, where A dagger is this. Of course, the summation will depend on what the rank is. If rho equal to n, A dagger will have n terms. If A rho is less than n, A dagger will have less than n terms. That was, as I said, the first series of questions. Then we raised a second series of questions. Now that we have seen that during the course we have found the answers to all the questions in the first series of questions. The second series of questions that we raised were the following. This involved the change of variables. For example, we had A x equal to b. We said we shall introduce change of variables where we call x as some p y, b as some p c, where P is n by n invertible matrix. We want invertible because from the x variable to y variable and y variable to x variable, we must be able to translate that problem. Then A x equal to b becomes A p y equal to p c, and therefore, P inverse A p y becomes C. So, if we can make P inverse A p as diagonal, then we get a diagonal system and we can easily solve it. So, the question that we raised was, under what conditions can we find an invertible, under what conditions can we find an invertible n by n matrix P such that P inverse A p is a diagonal matrix. Then this leads us to the eigen problems. We found this is connected with the notion of eigenvalues and eigenvectors. So, what was the answer that we got? So, we first said we introduced the notion of characteristic polynomial. So, the answer, the characteristic polynomial of A, which is defined as C A lambda equal to the determinant of lambda I minus A, must factor out as lambda minus lambda 1 into A 1, lambda minus lambda 2 to the power of A 2, lambda minus lambda k to the power of A k, where lambda 1, lambda 2, lambda k are real and distinct. Recall that we are asking for a matrix P. Since we are having real, we always think of real matrix P. Okay. So, all over lambda 1, lambda 2, lambda k we are seeking as real and distinct, these k distinct lambda 1, lambda 2 k, and A 1, A 2, A k are integers greater than or equal to 1, such that A 1 plus A 2 plus A k equal to. So, the first requirement is that the characteristic polynomial of A factors out like this. Then we call the lambda 1, lambda 2, lambda k as the distinct eigenvalues of the matrix A, and A 1, A 2, A k were referred to as the algebraic multiplicities of these eigenvalues. Then that was the first condition. Once that is then, so the conditions we are asking for, under what conditions, consists of many parts. The first part is that the characteristic polynomial must factor out as pointed above. Then 2, if we define W j to be the null space of A minus lambda j I for j equal to 1 2 k. These we called as the eigenspaces corresponding to the eigenvalue lambda j. If then dimension of w j, which we called as the geometric multiplicity, must be equal to. So, this is what is known as algebraic multiplicity. Geometric multiplicity is equal to the algebraic multiplicity. This must happen for for every for j equal to 1 to every eigenvalue, the geometric multiplicity must be equal to the algebraic multiplicity. These are the two conditions that A has to satisfy in order that the matrix P exists. So, therefore, given any real P, the real A n by n matrix, we ask the question, does A satisfy the above conditions? And again the answers can be yes or no. In the case of S, we asked, therefore, since it satisfies the condition, there exists a invertible real P n by n matrix such that P inverse A P is a diagonal matrix. So, our question was, under what conditions there exists a P such that P inverse A P is a diagonal matrix. We have got these two conditions. Now, we ask whether matrix A satisfies these two conditions, and the answer is yes. Therefore, there must be a P. What is that P is what we asked. What is such a P? And answer was as follows: let u11, u12 etc. u1a1 be a basis for w1. So, in general let uj1, uj2, ujaj be a basis for wj. Since the dimension of W by condition 2, we said that the condition is satisfied. By condition 2, dimension of Wj is Aj, and therefore, a basis for Wj will have Aj vectors. Now, if these Aj vectors are denoted by Aj1, Uj1, Uj2, Ujaj, and this we do for each j, then we set P equal to the matrix whose first column is u11 and go on u1a1, then u21 etc., u2a2 etc. In other words, P is obtained by putting these basis vectors along the columns. Then P inverse A P will be a diagonal matrix where lambda 1 will occur A 1 times and so on, lambda k will occur A k times. So, that is the case when P satisfies, when A satisfies the condition for the existence of a P. Now, what do we do when it says no? There were two alternatives. We said that one leads to the Jordan canonical form, but we looked at another alternative and we took this alternative in this course. We did not take the alternative course which leads to the Jordan canonical form. On the contrary, we took an alternative route which led to the singular value decomposition, because it also allows us to look at a rectangular matrix. Okay. So, what we did was the following. Instead of, remember, this question arose because of the requisition for the change of variables. If you look at the change of variables, we use the same matrix P for changing the variable x as well as changing the variable b. Can we not use two different change of variables like x equal to p y and b equal to p c, or x equal to q y and b is equal to r c, some change of variables. So, we asked this, if we change that, then instead of asking P inverse A P to be diagonal, we will ask Q inverse A P to be diagonal. So, the question is modified as, we cannot, if the conditions are not satisfied, we cannot get a real n by n invertible matrix P such that P inverse A P is a diagonal matrix. So, what do we do? So, we asked, can we get two real n by n invertible matrices Q and P. Q will be used to transform the variable b and P will be used to transform the variable x, such that Q inverse A P is a diagonal matrix. And the answer we got was yes, and therefore, what are Q and P? The answer we had was, you choose Q to be the matrix U, which was U1, U2, U rho, psi 1, psi 2, psi nu transpose. Remember, the U1, U2, U rho form the basis for range of A, psi 1, psi 2, psi nu A transpose form the basis for the range of A transpose. Since we are in the square matrix case M equal to n, so rho plus nu A transpose will be n, and therefore, this will be an n by n matrix. And not only that, this is an orthogonal matrix, and therefore, and Q inverse is U transpose, because U was an orthogonal matrix, and you choose P to be the matrix V, which consists of this V 1, V 2, V rho, and then phi 1, phi 2, phi nu A. This is again an n by n matrix, and then we have Q inverse A P is the same as U A V U transpose A V, and this we got as the singular value C S 1 S 2 S rho 0 0 0, and this was the singular value decomposition. This was the SVD. Then we asked the question that this can be generalized. Our analysis shows this can be generalized to rectangular matrices, and what will be our Q now? Q will be our U, but now an m by m matrix, and P will be our V, which will be an n by n matrix, and U transpose A V will be our no longer a diagonal matrix, it will have that S row cross row and the 0 matrix and all others are 0. There will be a leading diagonal block of S row cross row, which is a diagonal matrix with the singular values along the diagonal. So, S row cross row is simply a row by row matrix which has S1, S2, S row, all others are 0. So, you adjust, put a diagonal block consisting of S1, S2, S row and then adjust the other zeros, so that you get an m by n matrix. So, this is the general SVD. So, once again we have now found the answers to all our questions in the second series about diagonalizability. Under what conditions it is diagonalizable? We got the answer as eventually the algebraic multiplicity must be equal to geometric multiplicity, before that the characteristic polynomial must factor out and so on and so forth. And when it was satisfied, we knew how to find the diagonalizing matrix P. And when it was not satisfied, we said we can split it into two transformations Q and P, such that Q inverse AP is a diagonal matrix, and the Q and P were found in this format. And then we said that this could be also generalized to rectangular matrices, and we can get the general singular value decomposition even for rectangular matrices. So, that we have the complete set of answers for the entire set of questions in the second series of questions. The third series of questions, the third set of questions that we raised was the following. Suppose I have a vector v in Rn and a vector u in Rm, both non-zero vectors, okay, v u non-zero. So, suppose we have two non-zero vectors, then we defined the outer product or the tensor product, sometimes called tensor product. We shall define it now as follows: U tensor V to be the matrix V U transpose. Okay. So, in that case what will we get? We will get U is V is n by 1 and U is m by 1. So, we get an n by m matrix. If we take V tensor U, then it will be U V transpose, and this will be m by 1 and this will be 1 by n. So, we get an m by n matrix. So, if we take a matrix U which is in Rm, a matrix V in Rn and take U V transpose, it will be a m by n matrix. Then V tensor U is a rank 1 matrix. We then said we can take such rank 1 matrices and superpose them. So, the next idea we said was, if V 1, V 2, V row are linearly independent vectors in Rn, U 1, U 2, U row are linearly independent vectors in Rm, and then S 1, S 2, S row are positive scalars, positive real numbers. Then if you superpose all this, S j V j tensor U j, which is the same as summation j equal to 1 to rho S j U j V j transpose, is the sum of row 1 rank matrices and has rank row. So, the question that we asked was, can we write every m by n real matrix of rank rho as the sum of rho 1 ranked matrices. See, the construction that we have here shows that we can generate a lot of row ranked matrices by putting together these 1 ranked matrices. The question was whether we could do it and exhaust all the row ranked matrices, that is whether all row ranked matrices can be generated this way, which means can we write every row ranked m by n matrix as the sum of row 1 rank matrices. This is the fundamental question of decomposing a row ranked matrix into row 1 rank matrices, and the answer we got was yes, and the answer precisely yes, the SVD, we got SVD in 2 formats, and the sum form of the SVD gives such a decomposition. What was that decomposition? A equal to summation j equal to 1 to rho S j u j v j transpose, which can also be in our tensor notation written as S j v j tensor u j. So, therefore, we have the answer to the decomposition also. So, thus we have answers for all the questions we raised in the first 2 lectures and set them as our goal for this course, and since we are now all the answers, we have achieved our goal. All our goal was achieved, the main ingredient for achieving all these goals or all these answers, or what? Everywhere the same u j v j's will appear. The 4 orthonormal bases, we will write them down, V 1, V 2, V rho for the range of A transpose, phi 1, phi 2, phi nu A for the null space of A, u 1, u 2, u rho for the range of A, psi 1, psi 2, psi nu A transpose for the null space of A transpose, and S 1, S 2. Together with these 4 bases, we have S 1, S 2, S rho, the singular values. So, these are the main ingredients for finding all the answers. Therefore, given a matrix, these are the most important things that we have to compute with such a matrix. Where do we get all these from? Where should we look? So, the way to get this, let us recall, was the following. We first construct L equal to A transpose A, and then L is positive semi definite, and its eigenvalues can be arranged as lambda 1 greater than or equal to lambda 2 greater than or equal to lambda 2 rho greater than 0, which is equal to the remaining eigenvalues. When we dealt with positive semi definite matrices, we found that their eigenvalues can be arranged in this format, and corresponding to this we will get the the eigenvectors, orthonormal eigenvectors, which we call as V1, V2, V rho, and these are the eigenvectors corresponding to the null space. And then we defined S1 to be square root of lambda 1, S2 to be square root of lambda 2, Sk, S rho to be the square root of lambda rho. These were the singular values. Whenever we say square root, we mean the positive square root. Then we define Uj to be A Vj divided by Sj. So that A Vj becomes Sj Uj, and we can find that from this we can also get A transpose Uj is Sj Bj. And so we got the u's, we got the v's, we got the phi's, we got the lambdas, and finally get psi 1, psi 2, psi nu A basis, orthonormal basis for A transpose, for null space of A transpose by solving A transpose u x equal to theta m, and this can be done by elementary row operations. Thus, the basic ingredients therefore are mainly these u's and the v's. The phi's and the psi's can be found by solving homogeneous equations using elementary row operations. These are the easiest, but the question is about these V1, V2, V rho, U1, U2, U rho, lambda 1, lambda 2, lambda rho. S1, S2, S rho can be found the moment you get lambda 1, lambda 2, lambda rho. But we have seen that we can even get U1, U2, U rho the moment we get S rows, S1, S2, S rho and V1, V2, V rho, because the u's can be found from S's, V's and the given matrix. So, the crux of the matter therefore is finding lambda 1, lambda 2, lambda rho, V1, V2, V rho. Lambda 1, lambda 2, lambda rho are the positive eigenvalues associated with the positive semi-definite matrix L, and V1, V2, V rho are the corresponding orthonormal eigenvectors. So, when we learn computations, the main algorithms that would come into the picture are the computation of eigenvalues and eigenvectors of positive semi definite matrices. These are the most fundamental algorithms in computational linear algebra. So, now we have seen a complete analysis of a real n by n matrix. We will just ask a passing question, what about complex matrices? Complex matrices, the analysis will be almost similar. Only change that we will have to make is wherever we use transpose, we simply take transpose conjugate. So, the analysis is similar to the real case. The changes needed are the following. Replace transpose by transpose conjugate. So, transpose is, if we write it as T, transpose conjugate is written as star. What do we mean by this? For example, the real case and the complex case. In the real case, we define the inner product of two vectors as y transpose x. In the complex case, we will define the inner product of two vectors y transpose conjugate, which is y star x. And then if we have a matrix A, we look at the range of A transpose and the null space of A in R n, and the range of A and the null space of A transpose in R m. In the complex case, we look at the range of A star and the null space of A in C n, and the range of A and the null space of A star in C m. Then in the complex, in the real case, we found that the range of A transpose null space of A are orthogonal complements in R n, and range of A and null space of A transpose orthogonal complements in R m. In the complex case, the range of A star and the null space of A will be orthogonal complements in C n, and the range of A and the null space of A star will be orthogonal complements in C n. And we would have got u 1, u 2, u rho orthonormal basis for range of A transpose, V 1, we call V 1 V 2, V 1 V 2 V rho, and u 1 u 2 u rho orthonormal basis for the null space, the range of A. In this case, we will get V 1 V 2 complex case, V 1 V 2 V rho orthonormal basis for the range of A star, and u 1 u 2 u rho orthonormal basis for range of A. And phi 1 phi 2 phi nu A orthonormal basis for null space A. Here we will get phi 1 phi 2 phi nu A orthonormal basis for null space of A, and psi 1 psi 2 psi nu A transpose null space of N A transpose. Now, so it will be psi nu A transpose will be orthonormal basis for null space of A star. Now, where do we get all these things? Again, previously we considered L, in the real case we consider L equal to A transpose A, now we will consider L equal to A star A. Now, this will be positive from this stage onwards, it is all same. This will be positive definite, semi definite, and this will also be positive semi definite. And therefore, computations will proceed as before. Find the eigenvalue, the eigenvalues can be arranged as lambda 1, lambda 2, lambda rho correspondingly V 1, V 2, V rho, you get the singular values and so on and so forth. So, the necessary changes that we have to make in the complex cases are, remember we have a complex, in the complex case in the beginning itself, while defining the inner product, the geometry of orthogonality, there is a conjugation involved, and that conjugation reflects right through our computations all the way up to defining the L and all the bases, and then we get a positive semi definite matrix. So, all these analysis can be verbatim carried out to complex matrices now, and every one of the answers will be analogous to what we got. The one route which we have not adopted in this course is when the matrix is square matrix and it is not diagonalizable, what is that we can do, still getting P inverse A P only, not trying to resort to two matrices Q and P, but resorting to the same transformation P, can we make P inverse A P very close to a diagonal matrix. This is the Jordan canonical form theory in the case of complex and real matrices, and in the case when this is not possible, even when you have a general field, what we can do, these are questions for at a further advanced course in linear algebra, we have to consider a general field and analyze all these problems. But for a fundamental use as an engineer, most of these things that we have discussed will either appear in solutions of systems, or there in optimization problems, or in image processing problems, or in signal processing problems. So, these are the fundamental things that one will have to at least minimum compute with respect to a matrix. I hope these points will be referred to repeatedly and the basic necessity of these will be understood clearly.